Well, the answer is that when we have the slit twisted, that the beams that are making up the image come from different parts of the source. Therefore, they're not coherent. And because they're not coherent, they can't interfere. The zero order comes from the top of the screen as we see it there. The first order on the right comes from some distance lower down the screen. The second order comes from lower down again, and so on. They all come from different parts of the filament, and so they don't interfere. To me, this is the most convincing demonstration that the final image is due to interference. So, thus far, I hope you'll accept that the image detail in the final image is due to the interference of the diffracted beams, and the only parts of these beams that can interfere are coherent parts that have come from the same source. Let's now take out the slit. Go back to the pinhole for a moment. Take out the slit from the objective and look at the normal diffraction pattern once more. We know from the experiment with the iris diaphragm what happens when we take away the diffracted beams. We lose information from the image. The other way we can take them away is by taking the specimen away when we simply see the zero order beam. What I'm now going to do is to put in a small stop, a small opaque blob there, which I can arrange to be concentric with the pinhole. So I can push this in like an eclipse of the moon or the sun, and I can block off the zero order light. Don't worry about that little reflection that you see at the bottom. It's troublesome. I don't know what the cause is. I've been trying for about 5 years to get rid of it. It's a reflection from in the system somewhere. We'll return to the grating and put it back into focus because I've put a piece of glass in. We'll have the coarse and the fine gratings present together like that, nicely in focus, and in a moment I shall simply pop in the stop and show you what happens. Now I'd like you, before I do it, just to think what will happen when I take the zero order light away from here so that the image is being built simply from the diffracted beams rather than from the zero order plus the diffracted beams. Here goes. There you see the effect. The lines are now bright, the background is black. Take the stop out and the lines are now black and the background white. The notion is that the zero order light lights up the background. We know that if we withdraw the stop and take the specimen away, you see that the zero order gives you a uniformly illuminated background. Put the specimen in and take the zero order away, and you see that the diffracted beams give us bright lines in the positions of the diffracting features in the object, the lines on the slide. When you have in the positions of those lines a double dose of light taking the diffracted route together with light taking the zero order route, then those two lots of light, the diffracted light on the one hand and the zero order light on the other, interfere and give us the black lines. in order for this to happen, there must be some relationship between the diffracted beams and the zero order beam in order for them to interfere. Not only must they be coherent, but if they're going to interfere and give black lines, destructive interference, they need to be 180 degrees or half a wavelength out of phase with respect to one another. So we have the diffracted beams giving us light in the positions of the lines. We have the zero order covering the full background. When we have both sets of light together, we end up with black lines. This is a dark field image. There are more elaborate ways of producing a dark field image, but for the purpose of this demonstration, we're doing it illuminating with a pinhole in the first focal plane of the condenser and having what you might call an opaque pinhole in the back focal plane of the objective, which will block off the zero order light. Essentially, a dark field image is one to which the zero order light is prevented from contributing. Some people, when they see a dark field image, say that the contrast is reversed. On the basis of what you see before you at the moment, I expect you could agree with that. And at the moment the contrast is reversed, but that isn't the general case. Just to demonstrate that, here we have another grating on the slide where the contrast is already the other way round. When we put in the stop to get a dark field image, you'll see that the contrast is not reversed. So the general case is not that contrast is reversed. The general case, in fact, is that scattering features appear bright and the background becomes dark. While we're looking at dark field, let's move across to another grating on the slide, which, as you can see, is a very low contrast. It's a grating which consists of simply different thicknesses, different optical paths of material in the form of stripes, and also, and I'm sure accidentally, but very conveniently from my point of view, there are some little black spots on it which give me something to focus on. I could put the dark field stop in, but before I do that, of course, we'll have to focus the image with the extra piece of glass in. So there we have a focused image. You'll see, incidentally, at the top that even though the image is virtually invisible, we still get a diffraction pattern up at the top. Rather weak one, but we get a diffraction pattern. If I put in the dark field stop, you'll now see a dark field image of the object there, showing up the lines in good contrast. So it's easily possible to get contrast from what appears to be an otherwise almost invisible object. There, in the dark field case, we're building the image simply from the diffracted beams. If we try to build an image from the diffracted beams plus the zero order, there seem to be two problems. One, as you can see from the diffraction pattern, the zero order is very bright, and so it's swamping the diffracted beams, so they're not able to interfere in a fair way. But also, even if the zero order beam